I'm really delighted that when we created a Distinguished Fellows program here at the center, we were able to persuade Nobuo Tanaka, the former head of the International Energy Agency, to join the Energy Center as a fellow for the year, doing a series of work on the future of nuclear power in the US and in Japan, and as part of that, spending time in residence with us here at Columbia this week, and then he'll visit again in the spring. So we've had a wonderful week. I'm sorry this is the last day, and unfortunately this is, for a few months at least, the last day Tanaka-san will be at Columbia, but we've spent time with the Columbia community and with other folks in New York looking at the impact of the North American energy boom on the rest of the world, looking at issues of sustainability and the future of energy growth in China, and then this morning looking at the future of nuclear power with a really all-star cast. That's really a treat for us. So I'm going to turn it over to Nobuo Tanaka, and he'll introduce the rest of the panelists. Thank you.
Thank you, Jason. Good morning, ladies and gentlemen. I'm Nobuo Tanaka. I'm the Distinguished Fellow at the Center of Global Energy Policy here in Columbia. And today, I'm trying to moderate this very interesting issue about the future of the nuclear power, especially the day after the very interesting movie show of Pandora's Promise of the Robert Stone last night at the CNN. How many of you, by the way, saw the movie last night? Okay, not many, but certainly some people saw. Because I said in the previous seminars and sessions of Columbia, I urged people to see it because it's related to today's session. Because originally we planned to get Robert Stone to come here. He agreed to come, but because of this CNN broadcasting, he unfortunately cannot come. But instead, we have certainly a very, very promising panelist. From my left, Tom Blees. He is the chair of the Global Science Council on Global Initiatives. And he's a very good friend of Robert Stone. He will tell us about the story about the future of nuclear power, integral fast reactor, etc. And to my right, Miss Joyce Connery. She is the director at the White House and in charge of the nuclear issues. Thanks for her to come. Her statement is, of course, off the record, so nobody can quote her, what she's going to say here. And also to her right, from you to her left, is Dr. Yun Chan. He is at the Argonne National Laboratory, and you have seen the movie there in the Pandora's Promise. There was a discussion about integral fast reactor and pyroprocessing, and he's really experts in developing currently these pyroprocessing technologies. So he can tell you a lot. If you have any further question in this IFL, he's definitely the best person to ask. And also to the extreme to the left from your side is Ray Hunter. He is the ex-deputy director in charge of the nuclear reactor development at the Department of Energy. So he can tell us history of the nuclear reactor development of this country. So, having said that, I will first give the floor to Tom to tell us some history and future, what he thinks, and to open the floor, open the discussion and stimulate the discussion for that sake. And then I will give Joyce, and then Yun Chan, and then Ray Hunter. So Tom, please go ahead.
Thank you for the invitation, and look forward to a good discussion today. When we talk about the future of nuclear power, we're going to mainly focus on the first half century of the 21st century because there are a lot of things happening now that we really have to plan for, including an increasing population on the planet of up to 9 to 10 billion people. Now, sometimes people dicker whether it's 9 or 10, but I figure we better plan for 10. And if it's 9, so much the better. I wrote a book called Prescription for the Planet about 5 years ago, and the intent of the book was to produce a comprehensive plan so that by 2050 we could take care of raising the living standard to developed country standards for everyone on the planet and do so in an environmentally benign way. And it's not an easy task, but it's doable. And Prescription for the Planet basically laid out the plan in all its detail. And ultimately, we ended up creating a nonprofit international think tank called the Science Council for Global Initiatives. Now, I'm not, excuse me, I'm not trying to sell my book. If you go to that URL on the top, you can download it for free from our website. So, now, one of the things that we're thinking about is there seem to be two different views about the future when it comes to energy policy. And a very popular view is we'll all be very efficient and very virtuous, and we'll use a lot less energy in the future. But the other view is we should create an energy abundant world so that we don't have to depend on everybody being virtuous and using very little. Because let's face it, we have a very comfortable lifestyle. We use a lot of energy, and we're not willingly going to primitivize ourselves. And even if we will, the people in the street won't. So if we're going to have a real solution to the energy problem and other problems, we need solutions that allow people to act the way they sometimes will act. Now, a lot of you probably live in apartments, just as an example, in apartment buildings. And I'm sure you have recycling bins down by the dumpster. And you very conscientiously separate your recycling material, and it goes into the recycling bins. But when you go down there to dump your trash, I'm sure you see that in the dumpster there's a whole lot of stuff that should have been recycled because people's behavior. So what we want to do is create technological solutions so that people can behave as they will, and it won't harm the environment at all. Now, here's the population growth estimates that you've probably all seen this graph before. You can see that about 9.3 billion people is kind of the middle. So we're aiming for 10 here. Now, one of the problems with this is if we're going to have 2 or 3 billion more people on the planet, we're going to need a huge amount of water, because already there are many countries that are water stressed, and certainly if you add 2 to 3 billion more, where are you going to get the water from? And this is a problem that we can see how much energy it takes, how much effort it takes to provide water for a lot of people, because we've done a project in California with a water development project. I live in the Central Valley of California, which is that big green section. I live just west of Sacramento, kind of in the foothills of those mountains on the left. And the Central Valley is a semi-arid location. Looks like this when it's not being irrigated. We don't get any rain during the summer. We go 4 or 5, sometimes 6 months without any rain. But what's happened is the state of California has created a system of reservoirs to take the snow melt from the Sierra Nevadas and the other mountains around, and we have a fantastic canal system. This is taken right near my house. And they basically water the Central Valley, and in an area less than 1% of the land area of the United States, we've managed to create a garden that produces over 60% of the fruits and vegetables and nuts that are produced in the United States. So the same type of thing can be done on a global scale. If you go to agriculturalists and you ask them, how can you possibly provide enough food for another 2 or 3 billion people? And they'll say, well, yeah, we can do it if you give us the water. And so you go to a hydrologist and you say, well, can you provide water for that many people? And they say, sure we can if you provide the energy. So it all comes down to energy. One of the things about the energy, besides the fact that we're going to have to desalinate vast amounts of water in order to provide it for all those people, is you have to move the water around, because after the canals run for a while, it gets down and then you have to pump it back up the hill. The water project is California's largest consumer of electricity. But it works great. Now, some years ago, the Army Corps of Engineers and some other engineering companies came up with this idea for a North American Water and Power Alliance, where we would take water, divert water from the Mackenzie and Yukon rivers in northwest Canada, and we would run it down to essentially water the west side of the Great Plains and the western United States and the southwest and even on into Mexico. Doing so it's possible to do that, but they came to the conclusion that it would take at least 30 gigawatts of electricity to pump that water around, and that's an awful lot of electricity. So ultimately, the water problem can be solved, but it's going to take a vast amount of energy. Now, there are people who believe that we can get all the energy we need for 10 billion people from wind and solar primarily. Sometimes they include other technologies that aren't yet developed, but mainly wind and solar. And a lot of you probably have heard of Mark Jacobson. He's a professor from Stanford who had a cover story in Scientific American a few years ago about how we can get all we need from wind and solar by 2030. Now, it's not really realistic, but Mr. Jacobson is quoted frequently, probably more frequently than anybody, by people who are of the belief that we can do this. So I just want to give you a little graphic this is from Robert Stone's movie the other night, showing where we get our energy from in the world. And we got to remember all the time that it's not just the United States. We're talking about the entire world. We've only got 5% of the people on the planet. And although we use an inordinate amount of energy, we have to be looking at the global picture if we're talking about the future. So out of this small piece of pie of clean energy, you can see that wind and solar are extremely small, and yet people still believe that you can get all the energy you need out of it. Now, one of the ways that people like Mr. Jacobson come to their conclusions is they start with the assumption that everybody will use a lot less energy. They kind of disregard the fact that there's going to be 2 or 3 billion people starting from zero, and that over half the world now lives in relative energy poverty, and everybody wants a developed country lifestyle. Now, what I did was I took a sort of thought experiment. If everybody wants a developed country lifestyle by 2050 and we have 10 billion people on the planet, how much energy per capita would we use? And so what I did was I took the amount of energy that your average German citizen uses today. And the reason I chose Germany is a couple different reasons. One, Germany has embraced energy efficiency technologies probably more than any other developed country. And yet Germany has not offshored all their industry yet. So, and they use about half as much energy per capita as your average American. So it's probably a fair estimate, because even if Germany offshores their industry in the future, if we're talking about on a global level, the industrialization is going to be happening somewhere. So if you took the amount of energy that the average German citizen uses today and ramped it up so that 10 billion people could use it, and then you took the figures for producing energy with wind and solar that Mr. Jacobson uses, which are usually quite charitable in his favor, you would have to cover an area the size of South America with wind and solar panels. And I think it's probably pretty obvious that just from an environmental standpoint, this would be incredibly stressful on the planet, not to mention economically. Now, what we're going to talk about today is various types of nuclear power systems, but primarily the Integral Fast Reactor, which I wrote about in my book, which Yun Cheng was actually managing the project at Argonne National Laboratory when they developed it, so he knows all there is to know about it. But in this thought experiment, I looked at the footprint of what an integral fast reactor system with 6 modules, how much area that would take. And so if you wanted to produce the amount of energy that would take the entire continent of South America with wind and solar, if you want to produce that with IFRs, you would cover an area about the size of Buenos Aires. So it's a very graphic example of the concept of energy density. And I think it's pretty obvious that it's going to be a heck of a lot easier on the environment, and you're going to have a lot more reliable electricity if you cover an area the size of Buenos Aires. Now, the IFR was developed at Argonne National Laboratory West, which is now Idaho National Laboratory. We ran a reactor called the EBR-2, Experimental Breeder Reactor 2. The person in the center of this, Charles Till, was Yun's partner. He was the director of Argonne West at the time, and the two of them basically assembled the team that they had because they wanted to address all of the problems of nuclear power: safety, proliferation, waste disposal, economics. And the IFR this is a simplified design, but basically, unlike the kind of nuclear reactors we use today, this is a fast reactor, which means that the neutrons are not slowed down by water. And unlike the reactors we use today, which use pressure vessels, the integral fast reactor operates at atmospheric pressure. So basically, it's a pool design, and the reactor sits, or the core sits inside the pool, and then your steam generator is in a separate structure so that the radioactive sodium is not in the same structure where there's any water, because everybody knows the sodium-water interaction is not a good thing, so you basically engineer the problem away by doing this. Now, during the years of the IFR project, General Electric put together a consortium of American companies called, with Bechtel and Westinghouse and several other major companies. And they worked with the scientists at Argonne to develop a commercial scale design, which they call the PRISM reactor. And this reactor now has been offered, General Electric's offered to build 2 of these for the United Kingdom to dispose of their plutonium. The United Kingdom has the world's largest stockpile of plutonium, and they wanted to figure out how they could most efficaciously get rid of it, and the PRISM can certainly do that. Now, the reason they call it an integral fast reactor is because there's a recycling system that will be integral to the power plants. So essentially, you take all your long-lived nuclear waste, or what we call nuclear waste, all your actinides, the elements higher on the periodic table than actinium, the ones that have really long half-lives and that make the nuclear waste problem a million-year problem, and you keep recycling it, and you put the long-lived actinides back in the new fuel so that when you get finished, and this is just a mock-up of the recycling facility. It's quite simple because the type of fuel, the metal fuel that they developed, lends itself to very easy fabrication. When you get finished, you have fission products, which are nuclear waste, but instead of being radioactive for nearly forever from a practical standpoint, the radiotoxicity declines below the level of natural uranium ore in about 300 years. And it's in an inert form, either glass or ceramic, so that you won't leach anything into the environment for thousands of years. So it essentially solves the nuclear waste problem. Now, I'm gonna let it go at this because the other members of the panel, I'm sure, have a lot to say. we want to have time for questions. If you'd like to kind of keep up on IFR developments, you can check out that website. You can go to our sign up for our newsletter. We had a fast reactor conference last year with 9 countries represented. All these countries are very interested in building fast reactors, and virtually everyone in the nuclear power business understands that eventually we'll be using fast reactors and we'll be recycling our fuel. The question is, when do we do this? And my efforts are very focused on doing this soon. Fortunately, General Electric wants to do it soon, and many of these countries are anxious to do it as well. So, again, what we're looking for is an energy-rich planet where everyone's standard of living can rise, because one of the things that people say is, well, we have just too many people on the planet, and that's creating all this environmental stress, which is true. But in country after country, we see that as the standard of living rises, the birth rate declines. And so rather than having some draconian system to diminish the population of the world, instead, we uplift everybody, and hopefully that'll take care of the problem. I'll go back to Mr. Tanaka.
Okay. Thank you, Tom. Thank you, Tom, for the presentation or introduction of the story of this integral fast reactor. Yes, those who saw the movie found out that IFR was tested in 1980s about this total plant blackout situation or TMI situation, and they safely stopped. So there's a inherent safety mechanism there. On the other hand, also I want to comment on what Tom said, is that certainly energy efficiency is a very important element for reducing the burden for the supply side. And renewables will come, but certainly it may take time, and also cost is high. Because the discussion of the energy efficiency is everything is very easy to say, but electrification is happening. IEA has been seeing the forecast for the future, and in any scenario, then business as usual, or likely new policy scenario, or 450 sustainable scenario, or energy efficient world scenario, whichever the scenario, the electricity demand will grow. In the history of the humankind, electricity generation declined once in the history. And it is the year 2009, after the Lehman shock. Yes, the total global economic slowdown made the electricity demand decline once in the history. Even among the wartime, electricity demand grows. So this is the kind of nature, the electrification is the civilization. So in fact, how to make the electricity safe, sustainable, that is what we have to think about. And the technology is certainly the key. Having said that, let's move to the Joyce Connery for her comments about the current policy, nuclear policy of this administration. Certainly, President Obama is positively mentioning about the nuclear. New Secretary of Energy, Arne Moniz, came to Japan just recently. I moderated the session with him, and he was very clearly mentioned about the necessity and U.S. commitment for the future. But let's listen to Ms. Connery, please.
Said in the beginning, I know from personal experience how difficult it is to get White House lawyers to let people speak outside the White House. And so Joyce is here on the condition that her comments are off the record and not for attribution. So in terms of journalists who are in the room or tweeters who are in the room, please respect that so we can get government officials to come and speak at Columbia again. Thank you.
Oh, thank you very much, Jason, for the clarification. Please.
And so I can have further employment. Are there, just out of curiosity, are there journalists in the room? Okay, as I tell my children, hand check, hold your hands. No, I'm kidding. And just because I want to know who I'm speaking with, can those of you who are affiliated with the Columbia University system let me know who you are? Students? Interested public folks? Anti-nukes? No, I'm just kidding. Anyway, thank you for inviting me to come today. I am pleased to be able to accept the invitation. It was a kind of a last-minute opportunity for me to come here, and I'm happy to be back working with Jason again and David Sandalo, who worked with me for a while at the Department of Energy, and obviously Tanaka-san. I do want to just do a little bit of history about where I come from so that you understand my background a little bit. Full disclosure, my first employer in the nuclear field was Argonne National Labs, and I did work at Idaho National Labs, but I was stationed in Kazakhstan, where my job was to help shut down the BN-350 fast breeder reactor that was left over from Soviet days, which is a sodium-cooled loop-type fast reactor, and was challenging to shut down for a number of reasons. I'll save my comments for the specific IFR issues during the discussion period. I don't want to talk about any specific reactor technology at this point. I just wanted to give you an overview of kind of where we see things. My job at the National Security Council is in the International Economics Office, and I do energy policy on the international front. So luckily, I'm not the person in charge of our own waste issues here in the United States or our domestic policy. I'm also not the Iran or North Korea person, in case any of you were thinking about asking me challenging questions on that area. Most of my days are spent working with our interagency and talking to our companies to determine how we keep our nuclear industry alive, healthy, and a vibrant supply chain. So it's been about 2.5 years since the tragedy of March 11th, 2011 in Japan, and I think that's a day that will be kind of burned in our memories, and just like the big events of 9/11 and the assassination of Kennedy. Where were you when Fukushima happened? And where I was actually working for the Deputy Secretary of Energy at the time. And what was interesting to me, because it popped up on my desk first, and I got to go spread the news through the department and set up our emergency operations center and our 24-hour surveillance. But as soon as the word got out of what was happening at the Fukushima Daiichi plants, the telephone started ringing at our desks. And all of the contacts that we had in Japan over the years with whom we worked very closely were calling up to report situations, to talk to us about what it is that they thought was happening, what they needed, despite the fact that the country had just gone through a tragic earthquake and tsunami, and they didn't know where their families were. Their immediate thought was to contact us and to mobilize us. Additionally, Bernard Bergot from France picked up the phone, and he called the deputy secretary, and Sergei Kiriyenko from Rosatom called. And at that moment in time, it was clear that it was not just a situation or a crisis for Japan. It was a crisis for the entire nuclear energy field. And everybody jumped. They weren't worried about compensation. They weren't worried about liability. Everybody from the industry to the governments to the non-governmental organizations were setting up networks and trying to figure out how to get technologies, people, skill sets to that situation to stabilize it in a very challenging environment. So I just want to put that out there as a backdrop, because I think this was a kind of a different moment in time than we saw at Chernobyl, a different moment than we saw at 3 Mile Island, and I think that the mobilization of the community was pretty important. For our part, the United States has been pretty consistent since 3/11. After the Fukushima incident, President Obama spoke at the Rose Garden and restated the United States' commitment to nuclear power. He noted that when we see a crisis like the one in Japan, we have a responsibility to learn from this event and to draw from those lessons and to ensure the safety and security of our people. He asked the Nuclear Regulatory Commission to conduct a comprehensive review of the safety of all the existing U.S. fleet, at that time 104 operating reactors, in light of the accident. They did that, and they determined that there was no immediate safety issues. We continue to incorporate the lessons of Fukushima accidents into our approach to nuclear safety, both for our current generation facilities as well as our next generation reactors. But around the world, countries are making their own sovereign decisions regarding the future of their own domestic nuclear programs and weighing those decisions against energy issues, climate issues, and national security challenges. We've seen many nations come to the same conclusions as the United States, nuclear just makes sense as a reliable, affordable, and safe no-carbon energy option. When it comes to combating the ever more serious threat of climate change, we need an all-of-the-above energy strategy. And here in the United States, that's what we're committed to. Over the summer, President Obama gave 2 major policy speeches. The first was in Berlin, where he echoed the nuclear security vision he laid out in his 2009 Prague speech, calling on the global community to secure vulnerable nuclear materials, decrease the number of nuclear weapons, and build a sustainable and secure nuclear energy industry. The second policy speech was at Georgetown. I know I'm not supposed to say that in this room, but it was at Georgetown, where President Obama laid out an ambitious plan to reduce carbon pollution and begin combating the effects of a warming planet. These topics are linked by more than timing. Nuclear energy is an important source of clean energy, and to maintain political support for nuclear power, we must work tirelessly to protect against nuclear terrorism, prevent the spread of nuclear weapons, build a sustainable domestic nuclear industry. While we owe it to future generations to eventually eliminate the dangers posed by nuclear weapons, we also owe it to future generations to harness the power of the atom to produce low-carbon nuclear energy to fuel the engines of progress and prosperity. Nuclear is going to be an important part of our energy mix going forward. We're committed to supporting the American nuclear industry, which provides clean power to our citizens, creates jobs and export opportunities. As you probably know, about 19% of our electricity generation is from nuclear, but that makes up about 60% of our low-carbon electricity generation. But you also probably know that our domestic fleet is experiencing some challenges at the moment. On the one hand, we're building 4 brand new AP1000 reactors at Summer and Vogtle, and we have resumed construction at Watts Bar Unit 2. But there's a lot of pressure and a lot of scrutiny where every cost overrun, every delay is being written about, talked about, and complained about. The industry is not getting cut much slack after restarting after a 30-year hiatus. On the other hand, from Kewaunee to San Onofre to Vermont Yankee, we're shuttering reactors before the scheduled end of their design life. We're now down to 100 operating nuclear reactors and maybe below that by next year. Our domestic nuclear industry faces challenges of a deregulated electricity market and the low price of natural gas. New plant development, the predominant financial risks in new plant development are so associated with regulatory approvals, capital and construction costs, and a clearing price of generated electricity. Many of the utilities aren't willing to accept the risks. With existing plants, weak power prices, and an aging fleet that may need additional capital expenditures cause cash flow problems for the utilities. This is especially true in merchant markets where plants must use their earned revenue to cover maintenance and fuel costs and are thus far more vulnerable to low electricity prices. A decision to shut down a plant can create an easy solution to a cash flow problem. And just to connect this to the remarks that were just made about the IFR, I think that we have to understand that nuclear power plants are built in this country by utilities without a lot of government funding. We provide loan guarantees if necessary, but there's a situation of tight capital here with you guys being close to Wall Street. You understand that. And nuclear is considered still a risky business. So the decisions that are being taken by utility companies as to what their mix is. And the near-term situation is gas is cheaper. And with respect to my friends who are big fans of natural gas, it is better than burning coal, but it only gets you 50% to the carbon reductions. And we have to think about preserving that asset for future generations as well. Across the world, there are about 432 operating nuclear reactors in over 30 countries. There are 68 under construction. This comes from the World's Nuclear Association. One of the main drivers, of course, is the continuing concern over climate change and the need to address CO2 emissions. But many of these planned reactors are in new or developing markets. The UAE, the United Arab Emirates, they're the most recent entrant with 2 reactors under construction. These reactors are about 60 to 80-year assets and about a 100-year commitment from cradle to grave. Countries seeking nuclear energy must create an infrastructure with capable, well-funded independent regulators, an industrial supply chain, human capital resources, training and education programs, back-end solutions, and of course the capital to build plants. Additionally, and particularly post-Fukushima, public outreach and acceptance plays a large role in the ability to move forward with plans. This can be daunting to new entrants and investors. The problem with nuclear is you actually have to build it in a place with people with politics, and politics with, in our case, Washington. So it becomes much more complicated. On the other hand, nuclear energy provides other non-monetized benefits. It requires skilled workers, a supply chain, a regulator, a robust training and education system. These items are going to be additional costs that will be incurred while developing a nuclear power program, but they're also investments that will pay dividends in other sectors, raise living standards. It's an investment in future generations of scientists and innovators who will work on the next set of technologies and applications. And just a few words about one of the things that our government is investing in the near term is the small modular reactors. These are light water reactors that operate like the light water reactors we already have. They're smaller and we think potentially have a place in addition to the large reactors in the future energy market. The idea behind the SMR is not really a new one. We produce larger numbers of small units at a lower cost. Factory fabrication will enable learning effects that will drive costs down over time, a stable workforce performing the same tasks, improving with repetition. So think Ford Motor Company. This phenomenon is obviously not unique to nuclear. The Generation 3+ reactors, like the ones we're building down south, require large upfront capital investments that are not possible for all markets or all utilities. If realized according to plan and fully optimized, the total construction for an SMR plant could be in the order of $2 billion. Our large 3+ generation plant is on the order of $10 billion. SMRs can make nuclear more attractive to utilities looking for a portfolio approach to nuclear generation. The EIA is forecasting almost 50 gigawatts of coal plant retirements in the United States over the next decade, and SMRs might be suited to replace much of this capacity as a non-emitting baseload source. Other niche markets for deploying SMRs in areas where existing reactors are being decommissioned. They could be put online sequentially to spread the financial burden and benefit from a site that's already being used for nuclear power generation. Small modular reactors could be used in places where there's no options for larger non-nuclear power plants, where grid capacity and infrastructure are limiting factors. They're also being looked at for desalination projects. As we noted, the water issue is going to be big moving forward. But as we assess the role of nuclear in our energy mix, and in this case for SMRs, in creating a low-carbon future, we must be sure that we're focused on safety, security, and non-proliferation. We have the benefit of creating something new here and not retrofitting, so we must design the reactors with those attributes in mind. So in the interest of time, I'm going to stop here and let my other panelists have their say.
Thank you, Joyce. A very clear statement about the U.S. policy on the nuclear. And also, I thank you for mentioning about the Fukushima accidents. And I must personally, as a Japanese, apologize for that kind of big mess we have created. And also, I thank the U.S. to help us in the Tomodachi or friendship operation. And that was a really great support and at least the recovering part of the public awareness of acceptance of this technology. And I learned a lot by myself from Fukushima. Yes, there are many commissions for the investigation of the reasons of these accidents, and most of they are clearly saying this was the human error and could have been avoided if Japan was prepared enough for this kind of unthinkable situation of the tsunami. It was pity. It was a mistake of the operator. It was a mistake of the TEPCO management. It was a mistake of the regulator themselves, not doing enough safety regulation. It was a mistake of politician intervention too much. So there are many mistakes, but from that we learn and overcome for the future. But problem here is that in Japan, we don't have the luxury of shale revolution. So without nuclear power, Japanese industrial or competitiveness will be in difficulty, as well as it risks the national security. In case of the Iranian crisis, Japan owed a huge amount of oil from Middle East and also gas. So once something happens in the Strait of the Hormuz, Japanese economy will crash without nuclear power. And we are risking, currently no nuclear reactors are running in Japan, and we are risking every day of that kind of occurrence. And hopefully, Iranian situation will be improved in the near future. But we have to prepare for that kind of unthinkable but possible risky option. And I'm very strongly promoting the Japanese government that we should learn the lesson from March 11th. That is, we have to think about the unthinkable, because Iranian crisis could happen much more frequent than once in 1,000-year tsunami. And now we move to Dr. Yun Chan, because in Japan there are many people who are now saying about nuclear phase out because there is no solution for waste. And certainly this IFR has a huge safety, and also, as Tom said, about the easy management of the waste and non-proliferation power. So I will let Dr. Chan mention about these technical aspects of the reactor. Please.
Okay, thank you. Before I give some background information on the IFR, which Tom laid out very clearly, let me hasten to point out that in the near term, well, today, nuclear is providing 20% of electricity in the United States. And any near-term demand for nuclear to meet the increasing electricity demand will have to be based on current generation commercial reactors that are currently being built, and that will be the main reactors built in the next decade or two. And IFR is really next generation, beyond the next couple of decades. It was being developed at Argonne in the mid-'80s through mid-'90s as a next generation. As you may know, the Argonne is the birthplace of nuclear when Enrico Fermi and his team achieved the first controlled chain reaction in 1942. And Argonne developed basically all of the current generation reactors in the early stages, pressurized water reactor, boiling water reactor, that has been commercialized around the world. And Argonne has been basically looking at the longer term, beyond the planning horizon of the private sector, and also the risk and benefit is large that only the government funding can sustain the R&D. And Argonne developed the Integral Fast Reactor as the next generation concept because next generation requires three requirements. So I'd like to briefly describe how the IFR concept was to satisfy those three requirements. The first requirement deals with the magnitude of energy potential. Today's commercial reactors use less than 1% of uranium resources. The 99% plus is discarded as a waste, either in the spent fuel or in the tailings of enrichment process. And those are treated as waste, they are not utilized at all. In the IFR, we can use all of those remaining 99% of uranium by recycling, thereby extending the energy potential from the current generation nuclear reactors by 100-fold. So if, whether it's due to CO2 issues, climate issues, we have to replace fossil energy in a larger scale. Nuclear is the only option, and if that is called for, the IFR type of reactor that can utilize all of the uranium will be essential. That's the first requirement. A second requirement is as we envision a large-scale nuclear supplied electricity, the safety has to be further improved. If we have time, I'll talk about the safety perspectives of current generation as well as future generation, and obviously current generation reactors are safe, albeit Fukushima, TMI2, and Chernobyl, and it has its own unique reasons of why it happened. But in the IFR, we strive to make even better safety. For example, we demonstrated in 1986 a total station blackout scenario, like what happened in the Fukushima, in essence. In the Fukushima, reactor actually shut down. It was a scram to shut it down. and it was struggling to deal with the residual decay heat removal. What we demonstrated in EBR2 in 1986 was the total station blackout scenario, but the reactor was not shut down. Reactor is still operating 100%. And that means the coolant temperature will rise very quickly. That rising temperature means the thermal expansion of fuel assemblies, and that enhances neutron leakage, so chain reaction slows down, so the reactor is shut down by itself without the operator's action or any safety system functions. So this going beyond the current generation reactors capability, Fukushima, TMI2, and so on. And because the IFR is not pressurized coolant system, it's much easier to remove the residual decay heat by passive means, relying on the natural circulation of coolant and so on. So it's a much enhanced level of a passive inherent safety that we were striving for. And it was actually demonstrated in an actual reactor. And you would not imagine doing it in any other reactor in the world. The third requirement deals with the fuel cycle. In today's commercial reactors, the people, when I get into debate with the anti-nuclear, I'm glad there's no anti-nuclear people here in the audience. They mentioned that the nuclear industry is like a building house without toilets. And they're referring to the lack of back end of fuel cycle, the spent fuel, what to do with the spent fuel. It is very powerful metaphor. When I went to Germany, their metaphor was nuclear is like a plane taking off without the landing gear. So it has to be shut down immediately. So we have to wrestle with the back end of fuel cycle. In the IFR concept, we came out with the new technology called the pyroprocessing. Pyro means it's a higher temperature. It's much simpler than current commercialized aqueous reprocessing that's in operation in France, UK, and Japan, and Russia. It is possible because we changed the fuel to metal type, which the only reactor in the world which uses metal fuel. Everybody else, commercial reactors as well as future generation reactors, use ceramic oxide fuel. And we are the only one promoting metal fuel, and that allows the inherent safety, which I described, at the same time making the pyroprocessing also possible. And pyroprocessing has been actually demonstrated as a part of EBR2 spent fuel treatment program since 1996. That facility is still in operation. So the pyroprocessing has been more or less demonstrated on the engineering scale. The question is whether it can be applied to treat the current generation commercial reactor spent fuel, which is accumulating to large amounts. And we found that, yes, indeed it can be done. And we actually have what's called the CRADA, that's a Cooperative Research Development Agreement between DOE and the private sector. We found a sponsor, Landmark Foundation, who is providing the funding to come out with a conceptual design of such facility to treat LWR spent fuel at 100 ton per year scale. And what we're hoping to do is to come out with a conceptual design and the capital cost estimates, operating cost estimates, and so on, to facilitate a decision-making process to go to the next step, actually demonstrating it. And once the advantage of pyroprocessing is we can extract what's called the transuranic elements. These are the spent fuel has three components. Obviously, the fission product. These are ashes of nuclear fission, and they're typically about 5% of spent fuel. The remaining 95% is uranium, so we want to recover uranium for recycle, reuse it. But then there's also a small amount of transuranic elements. These are heavy elements beyond uranium, like plutonium, americium, neptunium, curium, which have a long half-lives. They last typically hundreds of thousands of years. And those are provide the long-term radiological risk. So in the pilot processing, we are recovering those transuranic elements, and then we can burn in the IFR. By doing so, we are reducing the effective lifetime of a nuclear waste from roughly 300,000 years to merely 300 years. So the waste management becomes much easier to manage, much easier to find a repository to put the 300 years life for waste than 300,000 years of life. So those are three major goals for the next generation reactor, and we have been developing IFR that meets all these three goals. So let me just stop here with that background information, and we can get into more discussions later.
Thank you, Dr. Chan. And also it is, I understand that because of its closeness, it is very strong in the proliferation resistance.
Yes.
That is a fourth feature of this reactor. But anyway, I think this IFR sounds like dream reactor, but why this reactor was not really actually built somewhere? This is a very interesting question. I always asking this question to Dr. Yun Chan. And I know his answer, but I want to ask this question to Ray Hunter because he was the director in charge of this reactor development in the Department of Energy. So why Department of Energy didn't take it serious to build this reactor actually at a bigger scale?
First, I'd like to thank you folks for coming, and it's an honor for me to be at this great university. Just as a little bit of background, I was at Wayne State University working on my PhD in chemical engineering when a friend of mine talked about a reactor they were building called the Enrico Fermi Atomic Power Plant just outside Detroit. And that happened to be the first commercial advanced reactor any place in the world. As a result of a stumble we had in 1966, we had a fuel incident. I had to go find a job. And I joined the Atomic Energy Commission and subsequent agencies and stayed there about 30 years. During that period of time, we looked at many different reactors, gas-cooled, molten salt, even as absurd as mercury-cooled. And we kept looking for what we thought would be the best advanced reactor for the future. And we were focused primarily on the mixed oxide reactor. And we built that reactor out at Hanford called the Fast Flux Test Facility. And we were moving to build the Clinch River reactor in this country, and it was decided that funding for that was not going to be sustained, and that got shut down. This motivated Argonne National Laboratory to look at the concept of the metal fuel reactor. And I became a convert after looking at the test results that they got in 1986, where they did the loss of flow without scram and the loss of heat sink without scram. These were two historic tests and confirmed to me the inherent safety aspect of this. But more important, it looked like the economics were going to be quite good in that if you ever look at casting metal fuel, it's very easy compared to mixed oxide fuel and much more economical. And then, of course, there was the proliferation issue. And Argonne took that on firsthand. And we believe we have a reactor design that will be very difficult, if not impossible, for proliferation purposes. Now, I can't say that there's no risk, but because any country can remove material from any machine and produce a weapon if they want to. But it's very hard on the pyroprocessing to do that, and you end up going to a Purex process if you really want to get pure plutonium for weapons. So I don't have much more to say other than I'm the resident bureaucrat and technocrat. My job was to defend the IFR budget. And I will say in 1986, we did decide to devote the resources of the department, and I was able to sway my management to sustain $100 million a year in the development of this technology at Argonne. And only through the lack of brilliance of our politicians, in 1994, they decided to cancel this, which to this day I'm still resentful of that decision because I think they made a very grave mistake. But having said that, I'm ready to take whatever abuse the government has in this problem.
Thank you very much, Ray. Because, well, so you mentioned that it's a political decision in 1994 to quit this dream reactor. In fact, Japan has helped to some extent of this IFR development when this reactor was taken very seriously in U.S. government. In fact, they quit helping because U.S. project stopped. Because this could be a very interesting option technically, as you mentioned, Dr. Chan, that this has been tested and proven already for this inherent safety as well as the easy management of waste, high-level waste, radioactive waste. I understand that there are certain people who, without knowing this technology, they say this is nuclear power is the residence without toilets. But if they know that technology already exists in the IFR, they cannot argue that way. Why? Maybe this question is Dr. Chan, only Dr. Chan, or well, it could be also Mr. Hunter, because why you are not really, I would say, making more presentation or showing this and to get more public acceptance for this reactor. Maybe this is also a question to Tom, that you have been doing a really a big work of this potential technology, but why public didn't react much more positively than it should be?
Let me first try to answer your loaded question. I am very frequently asked the question, if this technology is so good, why isn't France doing it? Why isn't Japan doing it? And so on. And that is, every time the question comes up. Actually, I introduced this technology in Japan in 1987 in a Keidan-ren, which is a large conference room. About 400 people attended. At the time, I did not know, but in the front seat, there were 4 top executives from Tokyo Electric Power Company, president, senior executive, senior vice president, senior president, vice president, and so on. And they were very interested in this technology, especially the pyroprocessing, because at the time, they were building a Rokasho reprocessing plant. That's about 800 ton per year reprocessing plant. And the cost was escalating. And it was up to about $25 billion to build a facility. So they were very interested in our pyroprocessing. And in the next 2 to 5 years, they committed utility companies in Japan committed $106 million to help the joint R&D. At that time, we did not do any engineering demonstration of any kind at all. Even then, they saw the potential and they committed $106 million of commitment, which was canceled when the program was canceled in 1994. Later, I went back to restart that collaboration, and they said, well, you canceled once, and who can guarantee it's not going to get canceled again? So at least the Japanese utilities have shown a great interest in this new technology. When I went to Europe with the same story, their advanced reactor program leader from Germany got up and was very angry and said their horse is in the river and they're going to swim or sink with it because they cannot switch horse in the midstream. So don't bother. I mean, they already made a decision. They have tens of billions of dollars infrastructure constructed. They're not going to abandon all those because the American has a new technology which has not been proven yet. So that's basically, that answers all these questions. Now, even today, when I make this pitch to U.S. decision makers, I'm not going to tell who, they say, what do the French say about this? What does Japanese say about this? I'm very disappointed that we are technology leader in the world, and we cannot make decision. We have to rely on somebody else making decision for us. And that is just, I just cannot understand that issue. But even today, that's the syndrome that we are living in. So that's, Tanaka-san, that's one level of an answer. There are many other variations that I can get into, but...
Can I take exception to that?
Yeah.
Sure.
So I just want to be clear, because I don't think it is that our decision makers are looking to France and Japan to make our decisions for us. I think this is a time of constrained budgets. I think that the Department of Energy has been criticized roundly for not being able to carry on large construction projects, and we have a great track record of not being able to carry out large construction projects within budget. And I think that the issue here is not that the technology is not sound, it's that it is not necessarily commercializable, I just made that word up, as of yet. Because it will take an investor who's going to take that concept and take it from bench scale or lab scale and put it into something that's commercialized, and they have to see that they're going to get a return on their investment. Part of the problem with these technologies is that the bottom fell out of the uranium market, and at the prices that uranium has, the once-through cycle is just more feasible going forward.
Yeah, I fully understand that. But sometimes nuclear is not only the cheap way of generating electricity, but more the national security technology, which Admiral Rick Over started some time ago for the submarines. So this, yes, I understand. For this must be done in a commercial venture, but sometimes, for example, Korea is very much keen to develop this pyroprocessing and light water integral fast reactor because they need to solve the problem of residents without toilets. They need to reprocess the spent fuel, which Japan is allowed to. Japan is a unique country who is allowed to reprocess even without having any nuclear bomb. In the world, there's no other country who can do legitimately the reprocessing. And Korea wants to do the same. Can you say no to them? This is a very interesting question. Now, US and Korea is doing 1, 2, 3 agreement revision, so it is on the way. But certainly this is a very high agenda for Korea to move into this technology. But anyway, I'll pass to Tom. You have something to say more?
Well, I just wanted to say that in terms of why this isn't presented to the public more, we just had it on CNN last night. I think millions of people saw it. So, so that was a big step last night. There are many elements of the status quo that have absolutely no interest in seeing a technology like this be deployed on a wide scale. When you think about it, we've got so much fuel out of the ground already that can be used as fuel in IFRs, from the spent light water fuel, so-called nuclear waste, old weapons material, but especially depleted uranium. We've got about 750,000 tons of it in the United States. There's so much of this material out of the ground already that's free, essentially. Some countries pay to get rid of it. France pays Russia to take a lot of depleted uranium from them after they do their reprocessing. That if we built enough integral fast reactors, we could power the entire planet for hundreds of years and displace all fossil fuels and even get rid of uranium mining as soon as we had enough of them running, because you wouldn't need to mine uranium, you wouldn't need to enrich uranium anymore. So, I'm not a conspiracy theorist. I'm not saying there's any conspiracy, but I'm just saying that in terms of an interest in deploying a technology like this, the most powerful industries on the planet certainly wouldn't like to see this happen. You have situations like even the railroad industry wouldn't like to see it happen. Half of the freight that's moved in the United States on rail is coal. That would all be done. You have state and federal governments that make a lot of money on a tax stream from fossil fuels, on royalties from extraction of fossil fuels. All of that would dry up because we've already got the fuel out of the ground. And then, ironically, you have in an unholy alliance with all the fossil fuel companies, you've got all the major environmental organizations in the United States that are fighting nuclear power. So, there's very few people that know about the technology and are saying, look what this could do for humanity. I mean, this has the potential to be as transformative as the Industrial Revolution. It can essentially solve humanity's energy problems. Unlike the Industrial Revolution, where we didn't have a clear view of all the things that would be invented that would be components of the Industrial Revolution, here we have a power system that we know can power the planet. And yes, there will be implications in terms of a transformation to such a culture, but we can see those up front. I mean, we can see that the coal industry, the oil industry, all of them would eventually disappear, and we can mitigate the negatives. But there would be so many positives because we would have a world where development is happening on a very large scale in all the developing countries. So it's a real system. It actually works. We've tested it out. We know it works. But there are way more elements of the status quo that just are rigid. And so we're going to have to keep talking about it, keep educating people about it, and hopefully eventually the pressure will be there for governments to make the decisions to actually deploy the technology.
Let me make one comment here. The decision in 1994 was not only on the integral fast reactor, or what they called the advanced light water or liquid metal reactor. It was a strike by the Clinton administration to kill all of nuclear power. They were taking away the next generation, and the current generation, they figured, would just fritter its way to zero. And that's the whole reason we went to store fuel, because there weren't going to be that many nuclear plants around. So we could build Yucca Mountain and just store it. Now, that's one man's view from sitting in the Department of Energy. I'm sure there are people in the administration who might disagree with that. One of them may be working in the Secretary of State, but it's important that we recognize that uranium has no use at all except to make weapons or make electricity. All the hydrocarbon is useful for other products, medicine, all sorts of other products that are useful to mankind and womankind also, I'm sorry. Uranium has no other use. I mean, you can't grow anything in it. It just makes wonderful electricity. And the amount of waste we're talking about when you take into account the IFR is piddling compared to what we've been dealing with coal waste and other things. So that's at least my belief, and I think we'll go to the IFR at some point. Whether I'm still alive, that remains to be seen, although I'm hoping for a long life. But it's going to be a struggle. As Yoon said, we're looking at 10 to 20 years. And I think it'll be 10 to 20 years before nuclear power actually starts on the ramp up again, at least in the United States. So,
Thank you. You mentioned that this, let's say, the light water reactor spent fuel is stored in the Yucca Mountain. But I understand that, so that means this is not disposal, but it is retrievable in a way to use in the future for the
currently, light water fuel is being stored in 31 states in this country. We've not put one spent fuel element into Yucca Mountain, even though we've invested, I don't know, $15 billion. It's causing the taxpayers about $800 million a year to $1 billion a year to pay for the legal suits that we have from all the operating companies for the cost they're incurring to store fuel on their site, which was never intended. And there are governors in certain states who would like to see that fuel taken out of there. And I think the Department of Energy hopefully will move to an interim storage site, which was part of a blue ribbon panel that President Obama put together to look at spent fuel. And that would be a plus for the IFR, because once it's centralized, the next step is to go ahead and build a facility like Yoon is working on and demonstrate we can process the material.
I see. I understand very well. Do you have any comments, Joyce, about the current policy after this Blue Ribbon panel or commission's recommendation or whatever, the request to the government to do something?
Yeah. So again, this is not what I do on a day-to-day. It's part of my day-to-day job. However, obviously, it has implications for how we talk to other countries, and the fact that to be a proponent of nuclear energy, you have to look at the toilet in the residence, to quote my colleague over here. One of the findings of the Blue Ribbon Commission was that we have to follow a consent-based approach. The challenge with Yucca Mountain, I think everybody understands, is that the Yucca Mountain exists in a place with people who have views as to whether or not they want this facility to exist in their state. There are other governors and municipalities and people who have stood up and said, we would be happy to take a repository in our state because of the jobs and what have you that are associated with it. I think that the point about a long-term, an intermediate storage is crucial, mostly because in addition to storing spent fuel on some of the operating reactor sites, we have spent fuel, I think, at 9 decommissioned sites. And for them to move forward on the decommissioning, they have to get that fuel off their site. The other recommendation from the Blue Ribbon Commission, which I think might resonate with folks, is that they thought that it would be beneficial to have whatever we decide to do in the waste done by another organization, whether it was a government corporation or something that was outside of the Department of Energy, because of the lack of confidence in the department to move forward on this issue. So I think that's also very important. There's legislation that will need to take place, so we'd need to actually have Congress move forward on some of these issues. And obviously, to be able to do that, we have to be able to get to the waste fund and use the money from that to be able to move forward on the waste issue.
Also, it is said that international cooperation or collaboration should be envisaged through this issue. Is that right?
Well, I think we have dialogues with countries all over the world with regard to nuclear waste. We've looked at the success stories. Finland and Sweden, for instance, had municipalities vying for a waste repository. But there's also the issue of originally we had low burn-up fuel. Our fuel is high burn-up now, so we have to look at what that means for long-term storage as well as for repositories. So there's a lot of work collaboration that can be done on the scientific level between countries on that space. But one thing about the integral fast reactor and the reprocessing, regardless of how many times you use the fuel, there's still high-level waste. So there's still always a need for a repository. So that's not an issue that goes away. It might become easier. It might become less of a long-term issue, but it's certainly something that we won't be able to dismiss out of hand. It will still have to be dealt with.
I think in that sense, also it is true that for the non-proliferation purposes, certain mechanism or framework, IAEA is the one, but certain mechanism of fuel supply chain and at the same time taking care of this waste issue or plutonium issue together in an international collaboration. Is that kind of idea is still alive?
I think we're still talking about it amongst several countries. France, for instance, sends fuel to other countries and they will take it back. However, they return the high-level waste. So there's still a back-end issue there. But they keep the plutonium because they have a MOX program. The Russians have a similar type program. We in the United States obviously have to fix our own spent fuel problem before we could even conceive of that kind of cooperation. But I think the idea of international fuel leasing is something that's still being talked about and considered, because I think it's the view of this administration that the spread of enrichment and reprocessing technologies is not a good thing from a non-proliferation standpoint. Those are the two processes that can get you to highly enriched uranium and separated plutonium, the two fuels for nuclear weapons.
Thank you very much, Joyce. It is very important because such kind of international program or cooperation is one way to convince the Japanese public, who is very skeptical after this Fukushima thing. But anyway, Dr. Chan, I think one of the issues is this cost for constructing the reactors. Do you think that, of course, for the testing or demonstration plant, it is very costly, but does integral fast reactor and pyroprocessing has a very efficient, very economical nature for the power generation option as a future?
Well, any not only IFR but any first of kind of reactors, next generation reactors, have to bear the first of kind engineering cost, first of kind of setup cost for the manufacturing facilities. So it will be very expensive. So that's why I said at the beginning that it's beyond the planning horizon of private sector. Also, the financial and licensing risk is beyond the private sector capability. But once we pass those initial first reactor, second reactor, and so on in maturity, once we get there, I don't see any difference between the IFR type of sodium-cooled fast reactor versus current commercial reactors in terms of capital costs. As far as the fuel cycle technology is concerned, pyroprocessing should be much cheaper than conventional aqueous reprocessing. So that will also make it more economically viable. But again, it comes back to, as Joyce said, there's a commercializable question. And that's the issue that no one in the private sector will provide such path forward. And that the first kind of risk has to be, I think, has to be borne by the government support. As far as, and I think in terms of a plausible path forward, at least in my personal view, we have to demonstrate the pyroprocessing first, because that's a lesser proven technology. And less widely known technology. So that's why we at Argonne is focused on this CRADA to do a conceptual design. And once we have a cost estimate for that facility, and that might be feasible to find a private sector financing source to construct such a facility. With the only caveat is once we do that, then we have to have a contract with the government, Department of Energy, to provide the reimbursement on the service basis, the dollars per kilogram we dispose the spent fuel down the road once the facility is completed. So I think that much is a private sector driven demonstration as I can envision. And then hopefully that will provide the impetus to, then we have to do something about the recovered actinide, transuranic elements that will provide impetus to demonstrate the reactor, first kind of reactor.
I see. So that your strategy of getting this IFR a reality is the first step is this pyroprocessing plant of 100-ton
Yeah, I think
capacity.
that should be the first step.
Okay.
Yeah.
Very good. Maybe let's open the, let's say, discussion to the floor. And I think you may have very much of the questions to the experts. So could you identify yourself and ask a question? Let's take one from David Sandalo.
Thanks for a great discussion. Two questions. First, could you comment on the proliferation issues in IFR? There was a brief mention of proliferation resistance in the IFR, but could you just expand on that and explain it? And then second, completely separately, on supercomputers and modeling and simulation as a tool, what impact do you see that having in the development of nuclear technologies in the years ahead, and you think that will have any impact on IFR?
Maybe Dr. Chan, I think.
Yeah, okay. On the proliferation aspect, it's mostly institutional issue. The safeguardability is tied to very closely to international issues. But technically, the intrinsic properties of pyroprocessing, let me just describe those. It is done in an argon inert atmosphere, and each operation is in a high temperature, 650 degrees C. So the facility is not accessible by human. And everything going in and out can have a very strong non-destructive assay capability to make sure no diversion is made from the facility. So from the security point of view, it's much easier. The process itself, we recover plutonium along with other minor actinides like neptunium, curium, and americium, which has a much higher heat source and also larger spontaneous neutrons, which will make the weapons a fissile. And also it has some residual gamma radiation, so the hands-on operation is not possible. So the material produced within the pyroprocessing itself cannot be used directly as weapons material, and that is one strong intrinsic characteristics. And so the process itself cannot be used to produce pure plutonium. But then that's not the whole story. We have to have a physical security, and we have to have a safeguard system that interfaces with the institutional barriers. Now, in terms of simulation, it will always help, but it cannot replace a real construction, real test, and so on. But simulation will help to understand the system better and so on.
Thank you. You have the question? And then go to there.
I'm here at Columbia, and I'm in the medical field. And in the medical field, we have some similar technology problems, like with malaria vaccine and with the HIV vaccine. And of course, those are the beneficiaries of people who are interested in technology and the market failure to bring the IFR to the market. Have you approached people like the Gates Foundation and the Buffett Foundation for this kind of a roadblock that seems to exist with the IFR?
It's interesting, actually. I visited with Bill Gates a couple of months ago, but he has his own idea of advanced nuclear, which is called the traveling wave reactor. The essence of it is you burn uranium in situ for a long time without the need for reprocessing. But then that brings a lot of technical challenges as well, like with the cladding, which in case the fuel elements has to last for 30 years and so on, and such material doesn't exist today. So the challenges are shifted from not doing the reprocessing to coming out with the new technologies that can last for 30-year fuel life and so on. I could not convince him the IFR was the way to go in this first round. But in time, we can come to, but at least he's using fast reactors, sodium cooling, metal fuel that we developed. So there's a 90% commonality in the technology, but the only difference in the back end is trying to extend the life. We're trying to recycle. I think we'll come to closure in a couple of years. In terms of market, it was interesting that obviously Bill Gates has interest in African, the malaria problem and so on. They're developing laser that can shoot at the mosquitoes 100 a second by laser. And the major carrier of malaria is mosquitoes, obviously. So he is trying to solve the humanity problems, and it's interesting that he's approaching with the nuclear as the reason he's interested in it is he recognized the need to have large-scale energy for the mankind, and that's why he's getting into it. So I appreciate your concern on how to reach the market. That's interesting issue. Yeah.
Also, I think, Dr. Chen, you said that Bill Gates visited Argonne to see the reprocessing plant.
I do not get the
Oh,
question.
you should not comment. Oh, sorry for that.
I do not get the
I'm
question.
so sorry. I'm ignorant of the rules. But okay, let's go to the next question. Please.
NASA for several years. And I've often wondered, since I first read about it through Tom Bleese's book, how much, and this is a question for Dr. Yoon Chang and for Tom Bleese, you've spoken in terms of, several people have spoken in terms of very high figures for a prototype. I was wondering from both of you, to the best of your knowledge at this point, what a prototype would cost?
If we do a modest size reactor like that, I'm talking about 100 megawatt electric or 150 megawatt electric, I think we can do it in the range of $1 billion for the reactor. For the pilot processing, the 100-ton per year, it's a pilot scale, so the commercial is about 800 ton. My rough back-of-envelope type estimate is about $500 million to do that demonstration. But these are my personal gut feeling type of figures, which have to be validated with a more thorough conceptual design and studies.
I just wanted to point out, as long as you're asking about cost, that there really isn't anything inherently absurdly expensive about nuclear power. And oftentimes, the people who are really against nuclear power argue about it strictly on an economic basis, Amory Lovins being the classic example. Now, the first two advanced boiling water reactors that GE built were built in Japan. And they were built in 36 and 39 months, and the overnight cost was about $1.65 a watt. That was in the mid-90s. China is now building AP1000 reactors, the first ones. The first two are due to come online next year. And they too say that they're coming in at around $1.60, $1.65 a watt. But they feel quite confident that when they get to the nth of a kind, when they get their supply chain in place, they can get it down as low as $1 a watt, which is extremely economical when you consider that in the United States, to build a reactor, we're talking about $8 a watt or more, $10 a watt. Why is this? Well, there are a number of different factors, from utility company regulation to, we could go into this all day. In the United States, why it costs so much money to build the same reactor. Now, some people say, well, China can do it cheap because they have low labor rates and maybe they're not being as careful as they should be. But in Japan, they have high labor rates and they import virtually all of the materials. So why could they do it for $1.65 when the South Texas project, which is a nuclear power plant down in Texas, wanted to add an ABWR to their power plant site? It was a design that was designed by GE in the United States, but they went to the Japanese to say, would you build this for us? So the argument that nuclear power is just not going to make it because it's uneconomical, it's simply not true. And they're being built in other countries all over the world. If it costs way too much money in the United States, we have to look at what those issues are, because a lot of those issues are just built in. They're just tacked on from all sides.
Thank you, Tom. The question in the middle. Oh, yes. You have the question also. Yeah. Well, after her. Please.
Thank you. I'm a student of economics here at the university. I think you made an excellent case, the panelists, for the potential of nuclear energy to provide for the energy needs in the coming decades for international development, particularly as Mr. Blees said. However, looking at the high growth regions of the world at the present time, many are relatively low income, South Asia, Africa, Latin America. How can these regions, where we will see in the coming decades rapid economic growth and growth in energy consumption, how can we make nuclear power cost effective on a sufficient scale? Not just building one reactor for show. If capital costs are expensive, as Ms. Connery said, where an SMR producing most a few hundred megawatts would cost up to $2 billion. Thank you.
Tom?
Well, at the moment, Russia is starting to build a nuclear power plant in Bangladesh, which is one of the poorest countries. And Russia has a lot of plans to build in developing countries. I'm not sure what the financing arrangements are with Rosatom, but I know that in the UAE, where Korea is building the nuclear power plants, obviously the UAE has a lot more money, but in that case, Korea has made the arrangement to not just build the plant, but also to operate the plant for its entire life. So I suspect that that's the sort of arrangement you'll be seeing in developing countries, and many developing countries now want to build nuclear power plants. Vietnam is intending to do it, and several others. Joyce could probably talk to you about that.
Look, I think that's an excellent question, and I think, again, we have to look at not just the cost of the power plant, but the infrastructure to support it. Even if a country is moving toward the build, own, operate model, which is, I think, what you were just alluding to with what Russia's looking for, Turkey signed some contracts in that realm, you still have to have the regulator in that country ultimately responsible for that reactor, and I think we always have to consider safety first. We've had problems in the United States with our supply chain having atrophied over the 30-year hiatus in which we weren't building, and even we've been having some challenges with delays with the current builds, both in China and in the United States, because of that. So I think it is a longer-term prospect, but it helps build the capacity within the country, but you have to make sure that country has the capacity. We're trying to match up universities here in the United States with countries that are moving toward nuclear to make sure that they have the engineering skill sets, that they have the technical skill sets, both for what we call lab coats and lunch pails, if they are going down the road of nuclear reactors. And there are countries in Africa who are looking at this very closely. Ghana is very interested in nuclear power. Obviously, Vietnam, as was mentioned in South Asia, is building at least 4, as far as we know, units to start, and they're looking to build some more. So I think we have to pay attention to this as this goes forward, but it's something in which those of us who are already generating electricity with nuclear energy have to be cognizant of. I know that the countries with whom we work closely, Japan, France, they also recognize this type of challenge and want to help build capacity in those countries that might be looking to nuclear for the future. And then just a comment about Bill Gates and his TerraPower venture. I think he personally and his organization are looking at this in terms of addressing the issue of what he calls energy poverty and making sure that there is a future capacity for nuclear and a type of reactor, and he's investing in this one particular kind, in which it could be used across developing countries and provide a future that's not based on carbon.
Thank you, Joyce. Please, in the 4th row here. Then go to the...
Just to your point, do you see any moves?
Could you identify yourself and then ask a question, please?
Oh, sure. Jeffrey Berman from Pyra Energy Group. Do you see any moves to ensure regulatory certainty over the long term, like 20, 30, 40 years, so that supply chains can be rebuilt and to make nuclear more economically sound?
I'm not sure what you mean by regulatory certainty. I mean, I think with the reactor designs that we have, the Department of Energy's project, NP 2010, helped license both the ESBWR, which is the latest generation of the GE design, which is supposed to be licensed relatively soon, and the AP 1000. And so we've been supporting those companies as they go through the licensing process. With the small modular reactors, we've got programs. Right now, B&W has a program with the U.S. government, with the Department of Energy, to help with that licensing. Regulatory certainty is always tricky because when you have a situation like Fukushima, there will be a re-look at the design basis threat that each of these reactors are looking at and making sure that you are actually meeting all the requirements so that there isn't a catastrophe going down the line. We have a good relationship now, I think, between the Nuclear Regulatory Commission and the industry who have these conversations back and forth to make sure that there is a probabilistic risk assessment approach to how to do nuclear regulation. But clearly that's a challenge. It's a challenge with the old reactors that have to retrofit. And I think with the new designs, they're building a lot more intrinsic safety features within them so that they will meet their safety requirements of the regulator.
Can I just comment, add to Joyce? I think there has been improvement in the regulatory process. It was enacted by Congress 10, 15 years ago. Basically, the improvement is three points. Number one, it's a one-stop licensing. We used to license construction permit first and then operating license later on. At each step, there could be an intervening process that slows down the licensing. But new regulation allows a one-step licensing, combine the construction and operating license. So that's a big improvement. Once you get a license up front, there's no further licensing required. And to go with that, also regulation allows the NRC to give a certification of a particular design. So this helps the standardization rather than having individual plant designed and licensed every time. Once you certify design, and that goes with a combined license application. So Westinghouse, for example, has standard design for AP600, AP1000, which is a pre-licensed more or less. Mm-hmm. And the third point is dealing with this early site permit. If you think you have a potential site, you get all the environmental permits done way ahead of time. So when the reactor project decision is made, you don't have to have it lengthen the process for. So this three-step improvement should streamline the licensing for future reactors.
Thank you, Dr. Chan. Yes, the lady and then back.
Thank you. This is a question about Japan specifically. So
Could you identify yourself first?
Of course. My name is Xian Wang. I'm a natural gas analyst at Barclays Capital. So from the industry side. And just quick question about Japan specifically. So you mentioned that there's a lot of geopolitical issues surrounding sort of the procurement of energy for Japan in the long run. So with the start of the LNG export, the refined natural gas export from the U.S. as well as eventually from Canada and the rest of North America, do you still think that will still be a problem for Japan? Do you think, if it's not going to be as much of an issue from a geopolitical side, will the Japanese government be more inclined towards eventually phasing out like the nuclear fleet of the country? So.
Well, the current situation after Fukushima is that the discussion now in Japan is very emotional and safety kind of concern from the public. So politicians cannot really take very, let's say, decisive position. So just they say, the government says, okay, let newly created regulatory commission makes the scrutiny of each power plant which now shut down to satisfy the newly, let's say, built the safety standards, very strict one. So probably the restarting of the power plant will happen towards next spring. The capacity of this investigation team is limited, so maybe 3, 4, 5, 6 is the maximum to see the first group of restarting. But eventually, the restarting is happening. Of course, all the reactors which exceed the 40 years lifetime, the utilities will think carefully if investing onto that doesn't make sense. Maybe some of them could be decided to decommission. But I think in general, for the mid to the long term, Japan do not have any, endogenous resources except renewables to some extent and nuclear. So I don't think there's no other option that for Japan of maintaining the nuclear power. Of course, the diversification of the sources or diversification of the route of fuel helps Japanese, security enhancement. If we depend too much on Middle East oil and gas, yes, we are in trouble if something happens. So we have to diversify our sources to Russia. We import 10% of gas from Russia already as LNG. Maybe we need more by building pipeline. And the United States exportation of the LNG will help dramatically because the price of Henry Hub is 5 times less than Japanese price or 3 times less than European price. So if U.S. exported, even we could buy the gas or LNG much cheaper than what we are paying now. So it helps to negotiate with other producers so we could have cheaper gas. So diversification's sake, for the negotiation's sake, U.S. exportation is very critical and important. But that cannot solve our problem in the middle, long term of nuclear issue. It helps, but cannot solve totally. So for Japan, for the energy security purposes, I strongly believe that nuclear is definitely necessary. Okay.
My name is Michael Gerard. I'm on the faculty of the law school here. I wanted to ask if any of you have run or are aware of scenarios of the time and money it would take to effect the kind of transition you're talking about. From what you've been saying, it sounds like commercialization of this technology is perhaps 2 decades away, and to actually build the hundreds of units that would be necessary and to build out the transmission network to bring that electricity to load is probably another couple more decades, and at a cost of several $100 billion. The cost is increased by the fact that nuclear power only produces electricity. Electricity is only about 40% of our energy use. So in order to really accomplish what you're talking about, we would also have to electrify our transport sector, our home heating sector, the other portions of the economy that do not now rely on electricity. So the question is, what if you were to instead spend that several decades and that several $100 billion developing an alternative scenario with a diversified portfolio of renewables that has wind and solar and geothermal and hydro and advanced biofuels, and also a great deal of attention to energy efficiency, not the sort of energy conservation that relies on behavioral changes, but energy efficiency through more efficient appliances and vehicles and industrial operations. Has anyone really compared those two scenarios? Because I think you need those two scenarios of time and money in order to make a rational choice between the two.
I'll grab this. There's a website called bravenewclimate.com run by an Australian named Barry Brook. And he has a lot of professional engineers and scientists that contribute to exactly that sort of discussion. So, and they've done a lot of studies on it. I would urge you to go to their website. As far as how fast we can build the PRISM reactor so that we can build IFRs, we're going to be discussing that next week in Washington, D.C. with Eric Lowen, who's a good friend of Yoon's and mine. He's the chief engineer for the PRISM project, and they've offered to build them for the UK. I think Eric probably has a little slightly different idea than Yoon about how fast it can be done. But that being said, even if that's a couple years, a couple decades away, we can build really good, very safe light water reactors today, like the AP1000, like the ESBWR, that can operate, it can shut down automatically, can dissipate the decay heat for days at a time without operator intervention. We can do that. We're building them now. China's building them. We're building them in the United States, and we're going to be building them elsewhere. The new light water reactor designs are very safe, and they're being built. So we can transition to nuclear power on a far greater scale already than we were doing. As far as instead of going nuclear, having a diversified portfolio of renewables, hydropower, there are new hydropower projects being done in Africa and elsewhere around the world, but hydropower has a certain limitations. In the United States, I don't think you could build another dam if you wanted to, even if you had a place to do it, because there's a lot of environmentalist resistance. In point of fact, the Sierra Club used to be pro-nuclear because they wanted to stop building dams until they changed their policy on that. But I think the graphic that I had there, where I described how you would have to cover an area the size of South America with wind and solar panels, I mean, and then your electricity supply is not nearly as reliable as it would be with nuclear power. I just don't see how that can be done. I mean, aside from the trillions of dollars that it would cost, the environmental damage itself would be staggering. So, wind and solar can produce something, but you saw that on the pie of energy, how tiny the wind and solar contribution is. Just one more thing I want to say about electrifying our transport, because a lot of people talk about how we have to do this. There's a gentleman who owns a trucking company who's joining our Science Council group, who designed an electric 18-wheeler. and he's been running it for a couple of years now. He gets 215 miles on a half-hour charge, but using lithium-ion batteries. But he recently was asked to come out to the Almaden Research Center, which is IBM's main research center in Silicon Valley, because they've made some breakthroughs with lithium air batteries, and they want him to test their lithium air batteries on his truck. They believe that by 2015 they're going to be ready to commercially produce batteries that could give his trucks a range of 500 to 600 miles. This will be a tremendously disruptive transportation technology because we will be able to electrify our transport. Now, there's a lot of different ideas for how we can power our cars. People say we should use hydrogen. Some people say we can use ammonia. And while they're technically feasible, you would have to develop, and in my book I talk about using boron, but for each of those systems, you would have to develop a completely new infrastructure. If we can do it with electricity, we've got the infrastructure already. All we have to do basically is be moving more electricity around. And we even have the capability to do that with a new type of wiring called ACCR lines, where you can take all your high voltage lines and restring them, essentially recycle them and string them back up, and you'll be able to carry over twice as much energy as we carry now on the same grid. So without building any new towers, you could double your electricity generating or transmission capacity, which I also wrote about in my book. The capability to electrify transport is certainly there. The capability to electrify home heating obviously is there. A lot of homes already have electric heat. So, and the capability to ramp up nuclear power is certainly there. France converted to about 80% nuclear power in less than 20 years while tripling their electricity consumption. And that was with old-style reactors that are much more simplified today, and like the AP1000, the SBWR, now they're much more modular. So if France could do that with no great sense of urgency, I lived in France myself, and I rarely used the term French and urgency in the same sentence. I mean, they drink wine on their lunch hours, but if France can do that without a sense of urgency, and we, on the other hand, now recognize the great urgency of climate change, and we have designs that we can use, standardized designs and modular designs, we certainly have the capability. As far as building enough IFRs, the manufacturing capacity isn't the issue. Actually, the startup fuel is the problem, because we need enough startup fuel. But it can be done, certainly.
Can I just be really precise about the conversation between GE and the UK, just because I like to be precise rather than vague? GE is not offering the PRISM reactor to the UK. I mean, the UK is considering technology options for managing their plutonium. This is not a power generation move on their part. They have a large amount of plutonium left over from legacy material that they need to deal with, and they're looking at GE's PRISM as an option, and they're also looking at the MOX program. So I just didn't want anyone to be left with the idea that this is a done deal by any means, that UK has not made their technology decision, and that this is primarily a management program from a non-proliferation standpoint and national security standpoint, as well as from a waste management standpoint.
Thank you.
No, but they did offer to build them. I mean, GE went over and offered to build 2 PRISM reactors as a solution to their plutonium problem. Right.
As they sell them.
Yeah. Yes.
This is not a prototype that they're going to build with their own money. That's all I'm saying.
No, the intent is to use Import-Export Bank and partner with a utility company in Great Britain.
Okay, thank you. Just add to some comments about this, the sustainability and need of the energy infrastructure. IEA, where I was the head of some time ago, shows lots of scenarios. And this shows that business as usual scenario to the new policy is kind of more likely scenario which each country committed at the Copenhagen COP actually introduce things, and then the CO2 emission will decline. Efficiency or renewables, etc. Efficient world scenario is, let's take much more serious measures for energy efficiency, and then CO2 emission will decline further. But actually, the sustainable scenario of containing the atmospheric temperature level increase to the 2 degrees Celsius for 50% probability, that is 450 scenario. So much more effort is necessary, and in fact, this is what is necessary from the likely scenario to the 450. End-use efficiency, power plant efficiency, electricity savings, fuel technology switching. So these all efficiency or savings are going to be calculated. More than half comes from there. And renewables, biofuels, nuclear, and CCS, carbon capturing and storage, is a very important technology to be deployed. And what is a necessary investment or capacity, power generation capacity to achieve this 450 scenario is this. You can add substantial amount of the capacity of all of the power generation to the 450 new policy scenario, and then on top of that, 450 scenario purposes. And what this actually means is really surprising. You have to build 16 gigawatts of nuclear power plant every year from now to 2050. You have to build 60 gigawatts of wind power plants every year from now to 2050. Same thing. Solar power plant, other CCS, enormous energy infrastructure is necessary to achieve 50% reduction or 2 degrees Celsius. Can we do this without IFR? That is what my point. But anyway, this kind of huge investment is certainly necessary, and this is a reality check, which IEA contributed to the negotiators of the climate change, by the way. The next question. Yes, please. Maybe.
I'm Joe Friendly, a video producer of a daily public access show, Truth for a Change. The Radiation and Public Health Project, as I understand it, has found statistical clusters of cancer downwind of virtually all nuclear plants in the United States as a result of regulators allowing what they call low-level radiation being emitted into the atmosphere. Is IFR an improvement on that?
Thank you very much. The radiation question is...
Yeah, I'm glad you asked that question. Actually, we are running out of time, so I'm not going to get into long discussion. But the radiation is a fact of life. We are getting, from the natural background, about 350 milligrams per year. Now, don't worry about this number and the unit, but let's say there's a natural background. It comes from radon gas coming off the Earth's crust. It comes from the skies, the cosmic rays. It's in the food we eat. Banana has some radiation in it. The water, drinking water, has some small amount, minor amount of tritium. So even some cosmetics we use, women use, have a radiation. You remember Xerox copying machine has the static, but now they use radiation to eliminate the static. So every copying machine has a radiation. Or the smoke detectors have an emission, it's a radiation. So it's everywhere. It's you cannot avoid from it. You know, it's coming from the sky, it's coming from Earth, it's in our body. Everybody's a radioactive body. But don't worry about sitting close to, because they are all beta rays, so they are all shielded by our tissue, so it does not go outside of your body. So the problem is we have we just live in radiation. Now, how much the nuclear power plant is contributing It's infinitesimal. Let me give you a number. The TMI-2 had a whole core meltdown, and all the radioactivity was released to the containment building. But containment building did its job, so that what came out of the TMI-2 is compared to the 350 milligram per year is about 1 to 2% of natural background. So instead of 350 milligram, you get 355 to 357, which is basically the same as natural. So even after major accident on TMI-2, it was only 2% of natural background. For normal operation, it's about 0.01% of natural background. So, so the downwind question and the tritium release, Long Island, Brookhaven, there were some years ago, there was big issues in the public about the tritium found in the groundwater and so on. They're all below the drinking water standard that Environmental Protection Agency has established. Because every water we drink has a tritium in it. It's just a minor amount, which is safe, which is below the all the natural background we are getting. So nuclear power plant does not add any new downwind, upwind. It doesn't matter. It doesn't add. It's totally not true. Even major accident, even Fukushima, where the entire inventory has been released and so on, outside the exclusion area, you can see the Pandora's promise that where they went around and measured the level. It's very close to natural background. Actually, 0.1 microsievert per hour, as the movie showed, is equivalent to about 100 millirem, which is about 1/3 of our natural background, because in Japan, you don't have radon gas and so on. You don't have coal mines produce a lot of radon gas. And New York, fortunately, has very little radon gas, so you have very little contribution of radon. But if you go to Midwest, especially West Virginia and so on, about half of this about 60% of natural background comes from radon gas. But nuclear power plant absolutely does not add radiation effect, health effects. Even TMI-2 accident did not add any to public population.
For about 15 years, I've been studying these issues, and I've looked at numerous studies, including the one that you were talking about, I believe. And there are a lot of people claiming that there are cancer clusters around nuclear power plants, but there are organizations like the World Health Organization and UNSCEAR and others who say that this is not true. And, you have to look at your sources. And I have not found a credible source linking cancer clusters in nuclear power plants. And in point of fact, there's a rather bizarre situation. In Arizona, the largest power plant in the United States is a Palo Verde power plant outside Phoenix. They don't use any water from rivers or anything. They're out in the desert. So they use wastewater from sewage treatment. And they found that they had radioactive iodine at the plant, and they couldn't figure out where it was coming from, and they were concerned because they're always monitoring it to make sure that no radiation escapes. They found out it was coming in the wastewater from people who were having thyroid tests, and they were having radioactive iodine injected so that they could do the thyroid tests, and then they were peeing it out, and it was ending up. So it was actually coming into the plant from outside. There are people now today, just within the last couple of weeks, I've been getting emails from people saying, oh my gosh, what's going to happen if the transfer of the spent fuel at Fukushima, if it doesn't work out, and it's going to blow up, and it's going to be an extinction event, and it's just absolutely insane, and it's because there's a anti-nuclear zealot, Harvey Wasserman, who's been writing this stuff, and people are freaking out. They're writing to me all the time for reassurance. There are plenty of people that are going to tell you that radiation is the scariest thing in the world. You have to look at your sources. And I would strongly suggest that you see Pandora's Promise. It'll be on iTunes next month. So if you didn't get to see it last night, you'll get to see it then.
Thank you, Tom. Thank you, Joyce. Thank you, Dr. Chan. Thank you, Ray. And I really appreciate that you come for this session and explain us about this, the current interesting issues. I learned this integral fast reactor just 1 year ago. I didn't know this reactor at all, even though I was doing nuclear business back in Ministry of Trade and Industry. And I learned since the meeting with Tom and Dr. Chan such a magnificent way of understanding new technology. But I feel always that the professionals like you should talk much more easy terms with people. Otherwise, we don't understand this difficult technology. So we still continue much, much further of communicating with all of you about the technologies and needs and policies in the future. And I wish all of you join me thanking all these panelists.
I want to say a special word of thanks to Nobuo Tanaka for organizing today's panel, for being with us here all week in New York. We're honored by his presence and by his affiliation with the Center on Global Energy Policy here at Columbia. We're sorry to see him go back to Japan, but he'll be here again in the spring, and hopefully you'll continue to come to our events. The next one will be next Wednesday, where we'll talk about the military and geopolitical implications of the North American energy revolution with General Stanley McChrystal, former head of armed forces in Afghanistan. Thank you.